Hi, and welcome to this fourth lecture of the module on differentiation and integration. In the previous lecture, what we were doing is we derived some of the integration formulae. These integration formulae were classified as Newton-Cotes integration methods, and the examples of Newton-Cotes integration formulae, the first one was the trapezoidal method, Simpson's 1/3 rule, and Simpson's 3/8 rule. Okay, what I will do today is derive the error equation for the Simpson's 1/3 rule. After going over the derivation for trapezoidal rule, Simpson's 1/3 and 3/8 rule, what we did was used Microsoft Excel to find integral from a to b. I think we did it from 1 to 2 if I am not mistaken, of 2 minus x plus ln x dx. That integration we did, and we used basically the trapezoidal method, the Simpson's 1/3 rule and the Simpson 3/8 rule, and we saw that when we used trapezoidal method with our h equal to 1, at that time there were significant errors between the actual integral value and the numerical integral value. Then when we chose h equal to 0.2, that means we split down the overall interval. So this is what we wanted to find out, this particular integral, or I believe the might have, the other line might have actually been closer to that. Okay, so we wanted to find this particular integral. What we did was first applied the trapezoidal rule directly to this integral, then we broke down this particular to this interval, then we broke down that interval into two intervals, and then we applied trapezoidal rule, and then we compared the results of the trapezoidal rule with the application of Simpson's 1/3 rule, and we saw that two applications of trapezoidal rule gives less accurate results than Simpson's one application of Simpson's 1/3 rule. Although the number of intervals that trapezoidal rule uses and Simpson's 1/3 rule uses are the same when we are going to break down the interval, the integration into two intervals for trapezoidal rule. Next, what we did was we broke down the same, instead of two intervals we broke it down into three intervals. And found out the numerical approximation of the integration using the trapezoidal rules, applying trapezoidal rules 3 times, once for this interval, second and third time for this interval, h being 0.333. Then we applied Simpson's 3/8 rule for a single application of the 3/8 rule, which uses the point y1, y2, x1, x2, x3 and x4. And we saw again that the Simpson's 3/8 rule results were more accurate than the trapezoidal rule, and were indeed more accurate than the Simpson's 1/3 rule, but the difference between Simpson's 3/8 rule and the Simpson's 1/3 rule accuracy was not that significant. We will take another example in today's lecture, a more chemical engineering example if you will. We will take that example to demonstrate once again how one would use the trapezoidal or the Simpson's 1/3 rule. Before doing that, I will again derive the error equation for the Simpson's 1/3 rule in order to show how the Simpson's, why the Simpson's 1/3 rule is actually fairly popular. Okay, so the polynomial that we are going to fit in Simpson's 1/3 rule, what we said we are going to do is between the value a, we will call that as x1, a plus h will be x2, a plus 2h will be our x3, which is our b. Okay, so this is what we said we are going to do. So we are going to fit a polynomial to this this data, and then we are going to integrate the polynomial that we fit. Now if we were to not stop at a plus 2h but go ahead a plus 3h, a plus 4h and so on and so forth, we will get a higher order polynomial. So a general polynomial p is going to be using the forward difference formula is going to be y1 sorry plus alpha times delta y1 plus alpha square sorry not alpha squared, alpha minus 1 by delta squared y1 divided by 2 factorial plus alpha minus 1 alpha minus 2 divided by 3 factorial delta cubed y1 plus alpha minus 1 alpha minus 2 alpha minus 3 by 4 factorial into delta cubed y1 and so on. Okay. So this is what our polynomial is going to be. If what we did in the previous lecture is we said that since the polynomial is only going to be fitted to this 3 data points, we will just retain these 3 terms, and the terms that we are neglecting are the terms over here. So because we are neglecting all these terms, there will be certain error that is going to be associated with neglecting those terms, and then we try to find out what that error is going to be, so on and so forth. That is what we essentially that part of it we did not do. What we did was only retain this particular term. What I am going to show today is that in the Newton's 1/3 rule, in fact this term also disappears when we actually do the integration, and the leading term that that gets left is this term. This term is h to the power 4 accurate. So when you integrate it, it will get Newton's 1/3 rule as h to the power 5 accurate. So the Simpson's rule, if you recall from the previous lecture, was h cubed accurate, whereas the 1/3 rule is going to be h to the power 5 accurate rather than h to the power 4 accurate, and that is going to be a very important property of these Newton Cotes formulae that makes Simpson's 1/3 rule actually more popular than the Simpson's 3/8 rule. Okay. So because people have done this derivation and we know what to expect, that is why I am actually going to retain this particular term and essentially going to replace this term with the numerical with the mean value theorem, and that term when we replace with mean value theorem is going to be alpha minus 1 alpha minus 2 alpha minus 3 by 3 factorial multiplied by h to the power 4 f4 dash of zeta, where zeta is some point that lies between a and a plus 4h. Okay. So that is what we get, where alpha, if you recall, is defined as x minus x1 divided by h. Okay. So that is the definition of alpha, and therefore the definition of therefore when we differentiate this equation we will get dx is equal to h d alpha. Again this is something that we have done in the previous lecture. It is not something that is new in this particular lecture. What we are actually going to do is see what happens when we apply the same methodology to the Simpson's 1/3 rule. Okay. So our integral I, the numerical integral I, is going to be integral from x1 to x3, which is h equal to 0 to h equal to 2, 0 to 2 y1 plus alpha delta y1 plus alpha minus 1 delta squared y1 by 2 plus alpha minus 1 alpha minus 2 by 3 factorial delta cubed y1 plus alpha minus 1 alpha minus 2 alpha minus 3 by 4 factorial h to the power 4 f4 dash. I will just write it a little bit, rewrite this. Okay. So the next term after this is going to be plus alpha, alpha minus 1, alpha minus 2, alpha minus 3 by 4 factorial h to the power 4 multiplied by f 4 dash of y, sorry, f 4 dash of zeta. Okay, that is our polynomial that we had over here. I have written that polynomial, and integral of that polynomial with dx is what our I is, and dx is h d alpha. Okay. So our dx was h d alpha. Remember what we want to do, our I is nothing but integral from x minus a divided by h, or sorry, a minus x1 divided by h to b minus x1 divided by h p dx, and dx is going to be replaced by h d alpha. So we have where a is nothing but our x1, so this is 0, b is a plus 2h, so so that is a plus 2h minus a, which is divided by h, which is 2. So that is why we get 0 to 2 p multiplied by h d alpha. Again this is something that we have done in the previous lecture. Okay. In the previous lecture we had considered all these terms, and based on these terms we had obtained the integral of the integral I using the Simpson's 1/3 rule, and that particular result essentially gave us h divided by 3 y1 plus 4 y2 plus y3. Okay. That was the result that we derived in the previous lecture. Now talking about this particular guy, we have integral from 0 to 2, this is alpha squared minus 2 alpha, sorry, minus 3 alpha plus 2, so that is multiplied by alpha, so alpha cube minus 3 times alpha squared plus 2 times alpha divided by 6, which is 3 factorial, multiplied by delta cubed y1 h d alpha is this particular guy, and this final term over here is going to be, we will write that as integral from 0 to 2, this is alpha multiplied by alpha squared minus 3 alpha, or this is going to be alpha cubed minus 3 alpha squared plus 2 alpha multiplied by alpha minus 3 divided by 24, and it is h to the power 5 f 4 dash zeta times d alpha. Okay. Now we will just consider the term, this particular term, and do the integration, and when we do that we will get integral from 0 to 2, one will have basically delta cubed h delta cubed by 6 outside the integral sign, and we will have inside integral it is going to be alpha cubed d alpha minus 3 times integral alpha squared d alpha plus integral from 0 to 2 alpha d alpha, or actually 2 alpha d alpha, sorry. Okay. This is what we will get, that we will be able to write as h delta cubed y1 by 6, this is going to be alpha to the power 4 divided by 4 minus 3 alpha cubed divided by 3, which is just going to be alpha cubed, plus 2 alpha squared divided by 2, which is just alpha squared, going from 0 to 2, okay, which we will be able to write as h delta cubed y1 divided by 6 multiplied by alpha to the power 4 divided by 4, which is 2 to the power 4, that is 16 by 4, that is 4 minus 0. So it is 2 to the power 4 by 4 minus alpha cubed, which is 2 to the power 2, sorry 2 to the power 3 plus 2 squared. Okay. So this is 16 divided by 4, which is 4, this is 8, and this guy is 4. So here what we have is 4 minus 8 plus 4, that is 8 minus 8, that is 0. So this particular term has become 0. Okay. So what has happened is, when we retain an additional term in this integration, when we actually do the integration and substitute the values of the limits of integration into this particular equation, what we realize is that after integration this term drops out. Okay. So the error is not going to be governed by this particular term, but in order to figure out the error we have to include an additional term over here, and that particular additional term is essentially this term, and then we go ahead and do the integration of this term to indeed see that after doing the integration that particular term does not disappear. So what we will write is h to the power 5 f 4 dash of zeta divided by 24 multiplied by integral from 0 to 2. We have essentially alpha to the power 4 minus 3 alpha cubed plus 2 alpha squared minus 3 alpha cubed minus plus 9 alpha squared minus 6 alpha. D alpha. Okay. So 3 minus 3 alpha cubed minus 3 alpha cubed is going to be minus 6 alpha cubed. So I will write down over here, and plus 2 alpha squared plus 9 alpha squared is going to be plus 11 alpha squared, okay, minus 6 alpha d alpha. Okay, which is going to be equal to h to the power 5 24 divided by 24 alpha to the power 5 divided by 5 minus 6 alpha to the power 4 divided by 4 plus 11 alpha cubed by 3 minus 3 alpha squared from 0 to 2. Okay. So this guy is going to be 32 minus 0 divided by 5, so it is 32 by 5 minus 6 alpha to the power 4 by 4, alpha to the power 4 is 16, 16 divided by 4 is 4, 4 multiplied by 6 is 24, so minus 24 plus 11 by 3 alpha cubed, so that is going to be 88 by 3, and minus 3 times 4 is minus 12. Okay. So this is 32 396 by 5 plus 88 multiplied by 5, 8 5 is 40 and 8 times 5 is 40, 440 divided by 15 minus 36. So this is going to be 536, this guy 536 by 15 minus 36, and or it is going to be minus 36 multiplied by 15. So 15 6 times 6 is 90, 0 9 carried over, 45 54. Okay. So what we get is 36 minus 536 minus 540, that is minus 4 by 15. So we will have h to the power 5 f4 dash of zeta divided by 24 multiplied by minus 4 by 15, this, and we get 6 over here, 15 times 6 is 90. So this is minus h to the power 5 divided by 90 f4 dash of zeta. Okay. So this is the error in computing the integral using the Simpson's 1/3 rule. Okay.